So I'm very pleased to introduce Sam McClure as a faculty candidate for the Center for Translational Research on Health Behaviors. Sam graduated from the University of Pennsylvania with a bachelor's degree in philosophy and science. He earned a Ph.D. in neuroscience from Baylor College of Medicine, with someone we all know, Reed Montague. Then served as a postdoctoral fellow at Princeton with Jonathan Cohen, who was just visiting here not too long ago. From 2007 to 2015, Sam was an assistant professor at Stanford University before accepting his current position at Arizona State University as associate professor in the Department of Psychology. His research and training are in cognitive neuroscience, and Sam's work has been influential in many ways. He's published in high-impact journals. His impact on me, he wrote this paper published this paper in 2004 in Science, and when I read it, I understood what I've been studying for 10 years at that point. I still refer to it as my Rosetta Stone. So it's a real honor to have Sam here and to talk about his current work. Welcome.
This is the strangest job interview I've ever had since I know everyone already. But it's great to see everyone again, so thanks for coming out. It's also, when I was putting together this talk, it was hard because I feel like too many people here know too much of my work, and so I put some work here in here. Two of the two main experiments I'm going to talk about. This is the first time I've ever talked about them, so if I stumble through and it doesn't make sense, just like ask me questions, and I'll try to clarify. Okay, but so what I thought I'd do today, well, I was very proud of this title, but I'm going to talk about the way I think that we understand time discounting now, and then the way I think that our current concepts that give rise to time discounting suggest interesting future research. So those are the two current experiments I'll be talking about. Okay, so first, so for the uninitiated, I thought I'd just spend a little bit of time just to go back a long time ago, like to the 30s, and the thought about this. So about time preference and where it comes from and how strange it is. So I thought a simple example. So I just was trying to think of my most recent purchase. So I just bought this T-shirt off the internet. I know it doesn't look all that cool, but I actually own that model of car, and this is, anyway, whatever. It means a lot to be this T-shirt. Hopefully it'll be at my house when I get home. But there are two shipment options for this T-shirt, right? So you can buy it on the internet at this specialty store, and I could have paid. I'm so used to free shipping that these seem crazy, but these were the actual shipment charges. So I got this one, $7.30 to arrive in 5 days, but you can also pay more to have it arrive sooner. And the point of this is not how ludicrously expensive shipping used to be and how much Amazon has changed our conception of this, but the fact that this doesn't feel all that odd to us that we pay extra to have things arrive sooner. And then this leads to the subsequent point, which is how odd this is. Because if you actually think about this, here's where the point of purchase, and then at some point later, the shirt will arrive, and you can start wearing it. It has some lifespan, right? You can wear it for, I don't know, how long do T-shirts last? A few years before your wife makes you get rid of them because it has a hole in it. And so really what you're paying for is, you're not paying for extra duration of being able to wear this shirt, but you're paying to have that duration, that wearing period start a little bit earlier. So basically you're trading off being able to wear the shirt in 2 years' time versus being able to wear it an extra couple days now. And paying extra money just for exactly the same thing, just shifted in time, is weird, and it gave rise to questions in economics, like where does this come from? So this is the initial point, which is, in the 30s was, well, people have these time preferences. They don't make a lot of sense, but if they do have these time preferences, then we should model it. And the model that came out was this exponential discounting, because the only way you can conceptualize this trade-off in a rational manner is to assume that people discount with some based on the interest rate that's available to them. So it didn't take long after this was proposed before people realized that this is not how people actually behave. And the best example to sort of illustrate how that this equation does not capture how people behave came in the following type of scenario. This is the real scenario that people considered. So this is sort of more personal. So imagine I have this choice. I can be economically, I can be careful with my money and being able to afford a really nice Christmas presents for my kids, or I can enjoy nice lunches and then not have money for my kids' nice Christmas. Does that make sense? Okay, so this is the choice you can have. Like, I can enjoy my life and eat sushi lunches, or I can save my money and be able to afford something nicer. Of course, I'm a dad, so my presents don't look like that. They look more like this. But it's the same trade-off, right? So nice presents with poor packaging, or more immediate enjoyment. And you could assume that my preference is such that I would prefer to be able to afford the presents than to buy fancy lunches, right? And then, so that's the blue line would be the presents, and the green line is the fancy lunches. And as time increases, the prediction is that as the delay to where they receive their value is going to decline. So the delay until being able to buy the lunch, or being able to, when you actually purchase the presents, or wherever Christmas is, the value declines. The standard economic model, of course, is that where the intertemporal trade-offs come on, where interesting behavior comes from, is when the consumption period for one good is shorter than for the other good. In which case, this will be consumed earlier, and you basically take this curve and turn it around because you're approaching it now instead of receding from you, and then the consumption period for the lunch is sooner, and so as you get closer and closer to lunchtime, the value of the lunch is increasing for you because the time delay to receipt. The presents are always much farther off in the future. Okay, now this is where the problem was, of course, is because this, the standard economic model says that you should, if you prefer the presents, you should always prefer the presents, and that's just the way choice would be. But it was noticed and pointed out that this is not the way people behave. And in fact, there used to be something called Christmas clubs. So this is back in the 50s where they wrote this. And Christmas clubs were these strange bank accounts where people could put their money so they did not spend it on things like fancy lunches. And they were zero interest accounts, and so you put your money in there, and they would not let you have access to your money until it was close to Christmas, so that you can afford to buy your kids fancy presents. Right? Does that make sense the way it works? Yeah, so you basically are using a bank as a way of hiding money from yourself. And these are called Christmas clubs. They're completely crazy that they would actually exist, but they solve a problem for us, which is that I may prefer to have the presents, but I find myself eating out fancy lunches much too often because they're tempting, right? And these kind of observations led to really what I think is one of the seminal contributions of psychology to decision science, which is this shift in the way of thinking about the way we value goods through time. So if this is the standard economic model, then psychology came in and said, well, the way we can account for things like Christmas clubs and impulse problems is you assume that the value in the future is a little bit less. So you'll see that this is sort of the standard economic model, this is the psychology replacement. The value of future rewards is slightly less than it ought to be. And this shift in the density of the value function is sort of shifted earlier so that you value immediate rewards slightly more than you should. And if you have this is called the hyperbolic discounting model because this functional form is a hyperbolic function. There's a free parameter here, which is the discount rate, which Warren has made hay over for the past many years. But the cool thing about this equation is that if you do the same trick of flipping this equation around and then making one of the rewards sooner, then you can get these interesting behaviors where as you approach the non-preferred outcome, its value will start increasing rapidly until you get a crossover point, such that you may initially prefer to be able to afford your kids fancy, nice Christmas, but then as it gets near lunchtime, you're trying to decide what you want to actually eat, you eschew the cheap, not so tasty lunch and go for the fancy sushi because it's so appealing. Okay? The psychological theories for why this occurred were sort of, again, there's a long tradition in sort of the way people thought about this. The standard notion was that there's something special that occurs when you get near or approximate to a reward in time. So, and in particular, this is an old idea, you know, Freud and, I mean, all the way back to the Greeks, thinking about when you get proximate to a tempting reward, you get in this emotionally aroused state, and then you have this switch of your preferences based on this emotional arousal. So the prediction was that when rewards are way off into the future, you're sort of more in this rational, deliberative mindset, and then when you are confronted with approximate immediate reward, it sort of triggers this emotional response that leads to this shift of your behavior in this sort of preference reversal kind of fashion. The prediction in terms of neuroscience was that this is exactly what happens, that we have executive processes that are responsible for future planning and conceptualizing and generation of abstract future goals and maintenance of those goals that are located in the prefrontal cortex, and that these may compete with sort of evolutionarily older basic reward motivational systems that exist in the ventral striatum and the medial prefrontal cortex and perhaps the posterior cingulate, and that it's the competition between these systems that actually gives rise to these self-control problems. We rely on the prefrontal cortex to help us plan and generate goals and figure out that I really do want to afford a nice Christmas for my children, but then we're tempted by this, where our behavior becomes controlled by these basic motivational systems, so that when there's an appealing immediate reward, it'll jump right, motivate our behavior in a completely different fashion, in a more emotionally driven fashion. And it's the competition between these two sets of motor control systems that may give rise to behavior. Okay? And so the prediction that came straight out of hyperbolic discounting and psychological theories of the way time discounting works is that there should be both of these brain systems at play, and it's the interaction between them that gives rise to behavior. And some of my initial work showed that this prediction actually matches out. It's not really worth spending time going through this, but these goal-related areas are sort of more insensitive to time than these brain reward areas, these motivational systems, and that when you're confronted with a choice between an immediate and delayed reward, it's the relative activity in these two systems that governs that seems to predict your behavior. Now, the way that the neuroscience thinking about the decision process takes place is based on has evolved since this time, and it's based on the known neuroanatomy that underlies motor control. So in the brain's motor system, we have our primary motor cortex, and that's under control of the basal ganglia. And the basal ganglia is this sort of structure here in the middle, and it receives inputs from around the cortex. And the general idea is that our cortex is busy trying to figure out what's going on in our world and how we should respond. And it feeds the various sorts of motor plans that we may consider into this premotor structure. And there's a selection that goes on within this motor structure, the output of which is sent to the motor cortex to actually generate our behavior. So if you want to understand decision making, really what you want to understand is the nature of these inputs, what are they sending, and how is this interaction occurring. Okay, so the previous work said that there's a difference between the motivationally relevant inputs, which tend to be the more ventral part of the basal ganglia, and these executive control processes, which tend to come into the more dorsal parts. So if you think that this is the way decision-making occurs, is through the interaction of the competition between these different motor commands, then you should be able to look for echoes of this in terms of brain anatomy. In particular, we know that different cortical areas send projections into different parts of the basal ganglia. It's organized in a topographic fashion, so that these more emotional areas project to more ventral parts of the striatum, and regions associated with goal planning and goal maintenance project to more medial and dorsal parts of the striatum. So there's a topographic organization between the cortical inputs to the basal ganglia. And then not only that, but recent technologies using diffusion imaging allow you to actually track these individual fibers. So you can measure the axonal pathways that go from executive control regions to the basal ganglia, and then from these more motivationally, the green ones, motivationally significant pathways. So what we have done since first identifying these systems exist is to actually go in and at an individual level try to measure these different pathways. This is what it looks like. So you sort of define the cortical regions of interest, do tractography to figure out where the axons are projecting to the striatum, and you can replicate known anatomy that's come from animal studies in a pretty remarkable fashion. And then once you have the different pathways identified, you can then quantify sort of the structural integrity of the different pathways at an individual level. And what we find is something like this. So we get this topographic organization within the basal ganglia. And then each of these dots represents a subject. So on the x-axis is the discount rate. On the y-axis is the tract integrity from this structure, and particularly the amygdala here, to the ventral part of the striatum. Okay, and then we just look for a straight correlation. And the prediction was sort of relatively borne out. I'll step through it. So one prediction is that regions in the dorsolateral prefrontal cortex or lateral prefrontal cortex, like the dorsolateral prefrontal cortex, ventrolateral prefrontal cortex, inferior frontal gyrus, that these are involved with goal planning, and that the more structural integrity you have, the stronger this pathway is, the better you should be at establishing and maintaining goals, and hence the lower your discount, or the more patient you should be. And that bore out more or less. You could see significant negative correlations across many of these structures. And then the other prediction is that these regions in the more limbic or affect-related areas, such as the amygdala, the anterior cingulate cortex, the medial orbitofrontal cortex, should have the opposite relationship, which is that the stronger they are at an individual level, the more impatient you should be, because the more greater the sort of emotional control should be. And that's also bore out, in particular for the amygdala. This seems to be the most reliable across our studies. Okay, so we started from general idea about how time discounting, what it is, how strange it is, how it seems to work, the seminal contribution from psychology, and then you break it apart into neural systems. And then this shows that once you have it broken apart into neural systems, you can start accounting for individual differences based on based on brain anatomy. Okay? So this is sort of between individual differences in discounting. There's also, this is sort of another experiment that I think sort of shows sort of our state of the art of understanding the brain basis or the psychology of time discounting, is that not only are there between individual differences in discounting, but there are within individual differences in discounting. So in different circumstances, we tend to be more or less impulsive. Alcoholics Anonymous has the acronym HALT, right? When you're hungry, angry, lonely, or tired, then you should watch out because you have a tendency to be, right? And that's true, right? If you're hungry, your discount rates go up. I'm not sure about angry. I'm not sure if anyone's tested that, or lonely. But anyway, probably tired has definitely been tested. Okay, so there's lots of within individual differences in discounting. To the degree that which discounting reflects clinically relevant outcomes, which Warren has shown repeatedly, understanding what gives rise to these intra-individual differences is important. So I thought just one example of the way in which understanding the brain systems involved in discounting can help you do this. I thought I'd talk about one of these that we studied. It's called the magnitude effect. It's one of the biggest effects within an individual on discounting. So this is sort of one of the first demonstrations of this by Dick Thaler. It's many years ago now. He had people, he said, imagine you just won a lottery for $15. How much would I have to pay you in 3 months to make it equal for you, right? And people on average said $30. So that's what this is showing. And then in parentheses is the interest rate, the annual interest rate on the bank account that would make $15 turn into $30 in 3 months. So 277% annual. If you could find a bank account with that, you should use it. You should sign up, right? So first thing he showed is that as the time delay gets longer, the interest rate demanded goes down, this is the feature of hyperbolic discounting. But the other effect he found is that as the dollar amounts go up, the interest rate goes down, which doesn't really make much sense. It's actually opposite. So if you think about like diminishing marginal utility, or then it actually has the opposite prediction of this. So this is sort of a strange phenomenon, but it's a huge effect. So discount rates go from 277, or interest rates go from 277 to 63 with time and also with amount. So it's a big effect on discount rates. There's really there's been no good theory about why it's true either. The theories that people cite are basically just a redescription, that there's increased elasticity in the utility function, which is basically just a really nerdy way of saying there is a magnitude effect. It's equivalent, okay? So we wanted to investigate this and figure out, well, can understanding the brain basis of discounting help you understand it? So we did the standard thing, which is we just put people in a scanner and scanned them and gave them low magnitude choices and high magnitude interrupted choices. Just to quickly go through the results, what we found, this is a slightly more advanced analysis because the times have changed, but we find that there's differences in activity, more activity across prefrontal areas for high magnitude choices than low magnitude choices. And this is really just an icon. Don't try to make sense of this slide. But that's what this is sort of like the final slide we had to sort of show this. The argument we make in this paper is that this is like an adaptive feature of discounting. Okay, so if you assume that that time discounting results from this interplay of different motives, there's this basic motivational system and then goal maintenance and generation. And if you presume that exerting cognitive control or exerting control over your behavior is costly, people don't like to do it, right? If given the choice, people just won't do it. It's effortful and costly. So if you presume that that's the case, then what we argue is that it makes sense that there should be a magnitude effect. Because if the stakes in a decision are low, then it might not be worth your time and effort to actually try to regulate your behavior in an important fashion. But as the stakes become bigger, then it is worth your time and effort, right? Because you're dealing with it's a more impactful choice. So what we argue is going on is that this is reflecting an adaptive switch in the strategy you implement into making your discounting, and you are more willing to engage control processes when the stakes get larger. Does that make sense? Okay. And anyway, Warren and I have talked about this sort of off and on. You talk about how, most of us, we go through our the healthy behavior is to go and regulate your behavior and have flexibility in the way you evaluate immediate and delayed rewards. And one thing that may happen with disease or with addiction is you become hyper-focused on the here and now and you lose this adaptability, right? So I can go with my kids out on the weekend and be irresponsible, but then I can come back and be fine. If you're sort of stuck in this irresponsible mode then that's not so good. Okay? So that was what we argued. One thing we've done is a sort of a follow-up to this, which I thought it was a good sort of conclusion to the sort of present state of affairs as I understand them, is we use TMS. This is a paper we're just getting ready to submit. So we just use low-frequency TMS to the dorsolateral prefrontal cortex to try to shut it down. And the idea was that if you recruit the prefrontal cortex in this goal establishment strategy, then if we inhibit that ability, then we should inhibit the magnitude effect, essentially, right? So that's what we showed. So the purple line is control choices or low magnitude choices, and then the green line is the magnitude. So at baseline, discount rates are much lower. If we do sham stimulation, which we flip the figure 8 coil around, so to stimulate the air, no effect on discount rates. But when we inhibit the prefrontal cortex for 10 minutes before giving them the 10-minute decision task, we're able to eliminate this difference in discount rate. So we're able to eliminate the magnitude effect. This also shows, this is not the greatest paper because it shows, what we were hoping to show here is with another within subject difference and show that there's specificity. So this one, it turns out that if you say, do you want, for example, do you want $10 now or $12 next week, right? So, or you can shift it and say, do you want $10 now and nothing next week, or nothing now and $12 next week? Does that make sense? It's called the hidden zero effect. If you put these zeros, so if you say $10 now and nothing next week, for some reason people get more patient. And we did a study on that, and we showed that it has nothing to do with the prefrontal cortex. So we were hoping that if you take out the prefrontal cortex, you'll have a hidden zero effect, and then it'll stay even if you stimulate. And we've got mixed results on it, just to be honest about this figure, which is that if you were to ignore this blue line, I'd be happier because I don't know how to interpret it. But the magnitude effect does go away. So understanding something about the brain systems involved in regulating discounting behavior across contexts gets you a handle on being able to manipulate and understand the psychology. Okay, so this is what I think of as the current state of affairs under the present of time discounting, right? Which is that we know that people like things now. We know that hyperbolic discounting captures this quite well. It's a seminal contribution of psychology and decision theory. We know that time discounting derives from the interaction of at least two different brain systems, one important for executive control, goal maintenance, and generation, and the other for more basic motivational value responses. And that intra and inter-individual differences in time preferences may be attributable to activity and brain anatomy associated with these different pathways. Okay, which I think is I'm kind of proud of this slide. It's a pretty significant level of understanding. Okay, but it's not enough. Okay, so the future. Okay, so I want to talk about two things that I think understanding the neural basis of time discounting allows you to do. So two sets of work. Okay, so question, what new predictions may be derived from understanding how the brain gives rise to discounting? One study I'm going to talk about is the relationship between discounting and habit formation. Okay, so wait a second, I'll tell you how this works. And then the second is, so this is sort of the interaction of a new psychological construct with time discounting behavior. And then the second is, if you understand the brain systems that are involved in decisions sort of overall, can you start studying the dynamics within these brain systems to understand how the decisions emerge through time? And if you can, then my goal for doing this at the beginning was to try to come up with a mathematical. My goal for a long time has been really want a math equation for self-control. And I think it's possible. So I'll try to show you how far we've gone on that. I just think it would be really cool to have on New Year's Day, instead of like, what should my resolution be, like just write an equation for it. Does that make sense? Okay. Okay, so habits. Okay, so what do we know about habits from neuroscience? Well, we know that when you learn a new task, that movements are planned very deliberatively and executed by prefrontal cortex. So you sort of figure out what motor plans you want to execute, and you sort of coordinate them and then generate them. Primarily driven the locus of control in the prefrontal cortex. But with lots of practice, this locus of control shifts down to the basal ganglia, to the striatum. Okay, so the question is, that, might this same effect occur with self-control? Okay, so if prefrontal cortex is really important for self-control, if you execute the same self-control behaviors repeatedly, might it become, through the same habit formation, it's dependent less on the prefrontal cortex and become a habit? Okay, so initially might it be dependent on prefrontal cortex function, but with practice become independent of willful control? Make sense? That this slide should be kind of boring, but I think it's really important because I think a lot of our self-control behaviors are of this sort. Like on my drive into work every day, I really love donuts, and I drive by a donut shop every day on my way to work, and every day I'm tempted by it. Every day, right? Like every morning I wake up and I face a decision. Do I want to go for a run this morning? Right? Every day at lunch I have a choice. What, healthy or not healthy? Right? So most of our really important self-control decisions are not these one-off choices. They're these choices we face repeatedly. And if things like habits become really important, then your history of making choices, how you make those choices. If I stop at the donut shop, okay, here's a better example. Also on my way into work is a Starbucks with a drive-thru, and there is an ungodly long line on the way at that Starbucks every morning. And every morning I'm like, those people are killing their savings accounts, right? Because, I mean, $5 for coffee every morning. And I guarantee you they have a habit where they wake up, they know they're going to get coffee, they drive to work, they stop at Starbucks, and they don't even think about it. It's become so habitual. And they're long-term, anyway. Okay, so this is really the set of problems I have my mind on, which is the effect of habits on our ability to make our ability to make these self-controlled, important decisions, and then what consequences are there for behaviorally. Okay. All right. So the task we chose, we use a slightly weird task. We could talk about why, but I'll leave that for the questions. But the task is a weird one. You have to press a button. You can get, I think the default choice was $10 today, or $20 today, sorry. And then you're presented with, would you rather have this default $20 today, or would you rather have $60 in 42 days? And then there's a time period, and then the green light comes on. You either have to keep holding the button or release it, and it's sort of counterbalanced so that if you keep holding the button, half the time you get the default, and half the time you get the delayed. Does that make sense? So it's an intertemporal choice task, but it's this weird version of one, but otherwise it's the same as what you're probably used to from Warren's lab. And we scan people. We had people do this same task once a week for 5 weeks. Okay, and we scan them on week 1 and scan them on week 5. And the presumption was that when they first show up, they're not going to, this will be a new task, novel task for them. They're going to have to figure out, what decision strategy they want to use. And then by week 2, they're starting to really figure it out, 3 and 4. And by the time they come in for the final scan, it's like old hat, right? They know exactly what they're going to do, and it should be easy. And this is roughly the time scale that people have used for studying of habits in the scanner in other experiments. So we basically stole this design from the literature as trying to study habits now in reinforcement learning task. Okay? Now, there are 2 things we wanted to be true, just behaviorally. One, your discounting rate should be consistent, right? So week 1, week 2, week 3, as you make the same choices, you keep making the same choices. You develop the strategy, but then you just keep implementing it. And that's more or less true. So each of these lines is a subject, and you can see that most of the lines are flat. Okay, so the discount rate they admit on week 1 is the same all the way through. But there is a difference in behavior. So if we figure out what their discount rate is, we can figure out how many choices are inconsistent with that discount rate. And so this is like the number of errors they make, something like that. And on week 1, they make a fair number of errors, and then it quickly falls down so that by the second, third, fourth, they're sort of at rock bottom. Okay? So we think that this is sort of indicative of this formation of habits. You start off, you're not really sure what your strategy should be, that's sort of volatile, and then as you figure it out, it just becomes kind of a more fixed thing. Another prediction we wanted is that we were after is illustrated here, which is that the brain value system, which people think of as sort of this integrative system, so it takes into account these basic motivational commands, but under the regulation of executive control, that these should reflect subjective value throughout the whole task. They should, no matter what, no matter where the subjective value is coming from. So this is week 1, and this is week 5. And you can see in both week 1 and week 5, we get this ventral striatum, medial prefrontal cortex, and posterior cingulate. And this is the conjunction. So these are voxels that are correlated with subjective value. In week 1 and week 5, you can see we're able to replicate this brain value system across the whole time. The big thing we wanted to see is illustrated in this slide, which is that as you go from week 1 to week 5, the prefrontal cortex becomes less and less important in the decision. And there are two ways of looking at this. We can look at which brain areas are more active on week 1 and week 5. And that's this straight contrast. And you can see lots of prefrontal cortex and posterior parietal cortex, sort of executive control network. If you look within these regions, within dorsolateral prefrontal cortex, you can see that activity is much greater on week 1 than week 5, sort of on average. And then if you look time point by time point, how it correlates with subjective value, you find that on week 1, sort of following the time course of the hemodynamic response, the dorsolateral prefrontal cortex is correlated with subjective value in this negative fashion. This is consistently seen in the literature. So the more dorsolateral prefrontal cortex, the more regulatory control you have on the value. So it's significantly correlated with value on week 1. But by week 5, there's no correlation with value whatsoever. So not only is activity going down, but it seems to have very little impact on this value calculation, at least from your ability to measure based on sort of correlated brain activity. Right? So we have evidence for that. Instead, what we find is that if we look for brain areas that increase from week 1 to week 5, we see this increased activity in the dorsal striatum. And its correlation with subjective value, it's not shown, its correlation with subjective value increases from week 1 to week 5. So we have this decrease in dorsolateral prefrontal cortex activity in correlation with subjective value, and a corresponding increase in activity in the striatal region that's targeted by it, in this more motor part of the striatum. Moreover, the degree to which people show evidence behaviorally of habit formation is correlated with the degree to which you get activity in this dorsal striatum. So this is the choice consistency measure. So the more decrease in choice consistency, the more evidence we think we have of habit formation. And this correlates with the amount of increased activity that's in the striatum. It's kind of weak, too few subjects to really make a strong conclusion about it. But at least it's suggestive that this shift from the prefrontal cortex to the striatum is causally important. Okay? And then finally, we wanted to see if this is true, then are there other more interesting behavioral consequences? And this, I think Warren will like even better. So here was the prediction, which is that if you form these habits, then you're not trying to figure out what your behavior should be. You have sort of more fixed choice strategy, which means you should be less labile. If I try to manipulate your choice strategy, it should be less effective. Okay, so that was the prediction, is that as people develop these habits, they no longer reason about how they should behave. And since choice framing tries to manipulate behavior by changing their choice strategies, then perhaps practice reduces the effect of choice framing. Does that make sense, the prediction? Okay, so the choice frame we went after was something called the date delay effect. And it works like this. Would you rather have $10 today or $12 next week? That's one condition. That's the delay condition. The date condition is, would you rather have $10 on April 19th or $12 on April 26th? Same choice. It's just that people are much more patient when you put dates. The discount rate goes way down. Okay? It's called the date. This is sort of the original data. This is the number of people choosing the larger later when it's in the date versus delay, and you can see the numbers are all bigger for the date. Weird effect, right? No, okay? The cool thing is that from week 1 to week 5, on week 1, we get a big date delay effect. Discount rates go way down when you say date. By week 5, it makes no difference whatsoever. So you're able to erase this. And we think that I think that this is the most important part of the finding, which is that as you establish a behavioral pattern, it becomes more fixed, and it's harder to move people around. And this, I think, has huge implications for behavioral change and intervention. Okay, so future directions from this line of work. So I really want to establish whether this shift in activity from the prefrontal cortex to the striatum is truly habit formation. It's kind of hand wavy at this point, but I think we could follow up and try to really, really prove that. And then I think this has important implications for behavior change, and I want to sort of start looking at those. In particular, if you
it should be hard to change a habitual behavior. But if you're able to, and you're able to form new habits with an intervention, then it should help that intervention persist. And if you can use this measurement of shift and activity from prefrontal cortex to striatum as a quantitative measure of the degree to which you formed a habit, then it may be an interesting covariate to look at with behavioral intervention. Does that make sense? Yeah. So that's why I'm excited about this line of work. How much time do I have? I have 20 minutes? I'll take another 10? Okay. Just want to make sure. Okay? So then this is the other study I want to talk about. Future time discounting part 2. Okay? And this is where I want the math equation for self-control. So I'm going to show you what we've done. Does that sound preposterous? It doesn't sound preposterous. You should be able to do it. Okay? And our starting point for this was this big and growing literature in psychology and neuroscience, which shows that in many, many choice domains now, decisions are made by, and I'll define what this means, accumulating evidence in favor of choice options until a decision bound is reached. So the idea is that you have different options available to you, and you consider them in turn, and as you consider them, you gain evidence in favor or opposed to choosing that option. And you sort of sum all this evidence up until you reach some critical criteria where it's like, that's good enough, and then you choose. Okay, and so this is the mathematical model, and it's optimal. It's the optimal choice strategy in many choice domains. And there's really excellent evidence that this is actually the way the brain works, that you accumulate different brain areas, reflect information about the choice options, they feed forward into premotor structures, which then integrate that information, and then a choice is made once the activity in these premotor structures reach a critical bound. Okay, and there are, obvious predictions that come from this, but harder choice, according to this model, harder choices should take longer to make because the evidence is more balanced, and so you're sort of constantly kind of trying to reach this decision bound. But the cool thing is that assuming these kind of models, there's a very well described functional relationship between difficulty and response time. Okay, so we wanted to see whether intertemporal choice looks like this and whether this may be a beginning to understanding the process by which these choices are made. The hard part is you need to be able to manipulate difficulty. And how do you manipulate difficulty in intertemporal choice? So in many domains where this has been studied, it's like sensory decisions. Are there more green dots on the screen or more red dots on the screen? And to manipulate difficulty, you just make the number of dots more similar or more disparate, right? For intertemporal choice, it's all subjective value. Like, how do you actually make it? How do you do it, right? How do you make it more or less difficult? So here is what we did. It was with 2 sessions. So we bring people in once. We estimate their discount rate using an adaptive design like Warren uses a lot. And then we estimated 2 things: what their discount rate was, and then what the psychometric function is that translates the discounted value of the delayed reward to the probability of choosing that. Okay, so this is for one example subject, this is a psychometric function that describes that person's choice in session 1. And then on session 2, we can bring them back, and we design choices to hit specific points on this curve. Particularly, we want choices where the probability of choosing delayed reward is 10%, 30%, 50, 70, or 90%. And the prediction is that difficulty is greatest at 50, and it falls off monotonically as you get farther from 50%. So these should be easiest. The blue dot should be easiest. The black is medium. The red is hardest. Okay, so 2-session experiment. 1, bring them in, measure their behavior, and then you can really target. And it's pretty easy once you have this curve to generate choices that for the red, the black, and the blue dots. Because there are these lines here, so all you have to do is choose any choice along this line. So, $12, whatever this is, $12 at 35 days would give you a 10% chance of choosing the delayed reward. So you have an infinite number of choices you can do, and it's actually a pretty straightforward experiment to design once you have this set up. Okay, so that's what we did, is we bring people in once, measure the discounting, bring them in twice the second time, and then we give them choices where we vary the discount rate. And then we're going to analyze their behavior with respect to these integrator models. Now, the cool thing about these models, like I said, is that you get this really precise relationship between difficulty, choice outcome, and how long it takes them to make that choice. And so this shows this is our best fitting model to show what this relationship looks like with intertemporal choice. The black line, which you can see sort of hugging here, that's the output of the model. That's the density function for the reaction time. And then the green and red are the actual choices. Okay, so what we did is flipped reaction times so that if they chose a smaller sooner, we made that reaction time negative. It didn't actually take the negative time. We just multiplied it by -1 to give you two curves. You could see that when the probability of choosing delayed reward is 10%, 90% of the choices were for the immediate reward and 10% were for the delayed, right? This is the distribution of reaction times as this weird shaped curve, and it's very well matched by the model. And then as you shift to greater probability of choosing delayed rewards, you get a shift in the density towards choosing delayed, but the reaction time matches all the way through, which I find really compelling because it's as though you're sort of figuring out something about the process by which the choices are made. Okay, there are interesting predictions that follow from this. So prediction number one is that you're integrating information, and the information you're integrating is the difference in the value between these two options. So if you think that this is the process that's actually taking place as people that drives these decisions, then you also are supposing that there's evidence about the relative value of these two options located somewhere in the brain. So we can look at that. This is the measurement of the relative information in the choice. And we find it again in this ventromedial prefrontal cortex, sort of classic brain reward structure. This is the mask from value signals across a huge number of tasks, this big meta-analysis. You can see there's not perfect overlap, but there's pretty good correspondence. So it makes sense. There's value information. It's the source of the signal. It's in the right location in the brain, which is good. The second prediction is that this information should be relayed to premotor structures and integrated. Now, the integration process is quick, over a couple seconds, which is really quick relative to the bold signal that you measure with fMRI. So what you end up really measuring with fMRI is the integrated, the area under the curve, area under the integration curve. And that's what we look for here. We call that total value accumulation. And we look for brain areas that correlate with this at a trial-by-trial level. Okay, so the way that math works to estimate a trial-by-trial level is beyond me, but I rely on a collaborator for that. But anyway, so that's what this is looking at, these yellow areas. We've gone back through, I didn't bring the data to show this, but here it looks like the entire executive control network plus some premotor structures. We've gone in with EEG now to look at a higher temporal resolution. And it looks like the real area of interest here is right here. So the dorsolateral prefrontal cortex activity does not show the expected ramping activity, nor does the posterior parietal, but there's beautiful ramping activity with difficulty over frontal central electrodes. So we think we have our handle on, we're starting to get a handle on this value accumulation process. I think it occurs in premotor structures, probably under the control of these executive control structures, which is what we think is really the critical component for self-control processes. So based on this, what we were hoping for and hypothesizing is that there's value signal generated down in these brain value areas. They're relayed up to this motor structure, premotor structure, where they're integrated to make the choice. But this integration process may be modulated by executive control process or regulatory process. So one way to think about self-control, therefore, is as biased value accumulation. Does that make sense? So if the decision process is this accumulation of this value signal, then self-control is the degree to which you bias that accumulation process. And we've actually gone and tried to estimate. There are many ways you can bias this accumulation. You're going to not spend forever on this slide because you can spend forever on this slide. But we can build in different ways in which self-control can work. It can change your attention to either the reward amounts or the time delays. It can change the degree to which you pay attention to one choice versus the other. Or it can change the lateral inhibition between these two things. So the degree to which, if one choice starts really looking better than the other, it actually suppresses the accumulation process. Okay, so this suppression accumulation process. This is what the suppression accumulation process looks like. This is for choice where you're kind of on the border. This is many runs of this accumulation process. You can see that, accumulation is kind of equal for the two options. And then as soon as the larger later choice starts dominating, it suppresses activity in the immediate choice. This is the model that actually seems to fit the distribution and reaction times the best. So if you just let this go free with all these different, this is what the model comparison is for all these different variants on the which are allowed to be free parameters. And the one that works the best is when you have this lateral inhibition, where as you're making your choice, you suppress activity in the other, causing this bias in the accumulation process. Okay? We're able to take this task and we look for brain responses that look like self-control. I won't belabor this, but it's the same sort of expected brain areas, lateral prefrontal cortex and parietal cortex. And then we look again at a trial-by-trial level to look at this lateral inhibition term, which we think is the basis for self-control. And we're able to map that again into trial-by-trial level, and it overlays really nicely with the brain areas that correlate with when you're making a self-control regulated choice. So we think that this is a nice mapping. You take just based on the choice outcome, what looks like people are exerting self-control, and then you go at it with the mathematical model, extract out trial-by-trial level parameters, and then look to the degree to which these overlap, and they overlap pretty nicely, as though you're really getting your hand on what's going on at a mechanistic level. Okay, so I went through that too quickly, but just for future directions on this work. We're just getting started, so we're just basic model comparison and trying to map parameters onto brain activity. But the next obvious step is you want to see whether you can manipulate self-control and whether you modify these model parameters as you would expect. And then if you do that and you have a better idea that this is really the mechanism by which self-control is exerted, then you can test whether these self-control parameters are different when you in diseases associated with self-control. So you start getting at sort of at a mechanistic level, the process level, what actually is why is self-control deficient in these diseases. And then once you have the ability to estimate these model parameters on a trial-by-trial basis, which we have, then you come and talk to Stephen and try to see whether you could look at this interaction directly and give people direct, immediate feedback on the degree to which they're actually exerting these self-control. And I think this is doable. And I'm excited about it. Okay? So that's all I have. I just wanted to say thank you to the students who actually did the work. So Wouter Vandenbos, Ian, Guki, Brandon, Christian, and Jesse. And this work was funded by NSF and NIMH. So thanks for your attention.
A couple of questions. I have one. So in this self-control model, will it be able to track the formation patterns?
Oh, in that one, we haven't built that in yet. I mean, we're just looking at a single session.
Yeah.
And I think there's no, it won't. But that would be an interesting future direction. That was a mean question. 2 independent lines of work. Yeah, but that's a natural, yeah, I like that idea. I hadn't even thought about it. And I don't know what it would look like. Yeah?
I work in ABC at the Institute, and we really move towards multi-disciplinary intervention to prevent COPD. And we recently done a study in my lab that was a single treatment intervention, and we found that there was spillover effect to other health behaviors. So if you focus on one thing at a time, you may other habits may
Yeah.
and I'm wondering if your ideas about self-control and habit formation, that you think that the multi-system approach where you're trying to change all these things at
good question. Okay. So, okay, so two things. One, the one thing I really like about trying to break apart time discounting into component cognitive processes is that it suggests a means by which you can get this cross behavior effects, right? So if you get people to, for example, be more future oriented, then it should have widespread ramifications, right? Because that implicates time discounting, but also a host of other health behaviors, all sorts of behaviors, right? Because it's a core cognitive process that probably applies across. I think the same kind of thing probably works for working memory, a number of things. Okay, so that's one why I think it's a cool idea, target a specific general cognitive construct, and then it has broad implications. Now, about habit formation. This is a big topic right now in cognitive psychology, right? Because people are trying to increase general cognitive abilities, increase fluid intelligence by giving people like time on lumosity, for example, right? Just get them to do cognitive tasks over and over. And it's controversial the degree to which you actually have generalizable effects, right? Some studies it works, other studies it doesn't. And I think one reason why this might be is because of the habit formation. So as you do the same task over and over and over again, after a while you're not really testing your work, you're testing some sort of codified, simplified heuristic that you're relying on that's no longer the sort of the general executive function, which is related to this habit formation process I think it occurs. So as you go through and you sort of chunk the task down into simplified thing, it may not be having the generalized effect. So I'd be a little concerned that habit formation would work against you, except for the target behavior, but I have no basis to say that other than my wild speculation. Not terribly wild, but it is speculation. Make sense? Vika? Yeah, the date delay? Yeah. Whole task, yeah.
I would think that maybe when you asked me at first, you wanted in April 1929, I might have connected with something with 29, that's why I did it.
Yeah.
Because the dates differed with me because you did people with C. But then when you did do that next week, the dates are 29. If you asked me if you wanted the 29 or the 30th, like not the 30th, but the 30th May, then maybe whatever made me wait for the 29 will come back to me, and that's why I wanted the 29 today.
Oh, I see.
So that maybe I had like an event or something that maybe
Yeah, so every week they came back, the dates shifted, right? Because they were all relative.
So the first time that they
Ah.
might affect my thinking
Yeah.
of it or make me wait as expected.
Yeah.
But then with time, every time that it comes in and I don't get anything, I'm actually still working again, it might be not only habit, but it's just like
Yeah, no, I'm with you. And
before it didn't come.
yeah, and I think this is, so we try to avoid that kind of thing. But I know you're trying, in your intervention, you're trying to tap into that, right? So there are different ways that dates can work, right? One is they can bring up specific future events that you then can elaborate on, sort of this episodic future thinking, right? So if a specific date has significance for you, then you can elaborate on it, right? So people who use dates in this way, like Jan Peters in his work, they use like the birthday or, like important dates, sort of to trigger people to think in a sort of a more detailed episodic fashion, right? Sort of really elaborate on that future date. We tried to avoid that. We just used like as random as possible, which is sort of the original Daniel Reed. It was, yeah, no, but we didn't use, we used like just randomly selected number of days between 14 and 45. So that was, and then we converted that into a date. And it certainly was possible we chose dates that have significance, like they're salient dates and they induce elaboration. We tried to avoid that, and we just used really just random dates, right? Does that make sense? But I think you're hitting on something which is, so I had in there at one point like parentheses, at least 2 systems. And I think, because I think this episodic future thinking and elaboration and sort of, it sort of feeds into construal level theory kind of ideas too, right? As you really elaborate the future, that this is an important component of goal maintenance and motivation. And we haven't really, my lab hasn't really jumped in on that, even though I think it's an unbelievably important direction. And you guys have done great work on it and others. But I think it's a different sort of set of processes. And even though they both might use dates, we're trying to avoid that. We have been.
Our time is up, but
Sorry,
Sam, in a couple of minutes, so if you have a question, you can come and approach him. And join me in thanking Sam for an outstanding presentation.